Let's look at slip caused by glide motion of a dislocation. Now, the main role of dislocation in plastic deformation is that when a dislocation moves across a slip plane, when a dislocation line moves across a slip plane, let us say that this box is representing a crystal, and here I put a dislocation sign with a positive as dislocation, and if this positive dislocation crosses this entire slip plane, then the result of this will be that the top half of the crystal translates with respect to the bottom half by one Burgess vector. The shift is one Burgess vector. So this is an important role of the dislocation line movement. Now we just want to make this a little bit more precise. This concept can be made a little bit more precise. So let us say that this dislocation line has a Burgess vector B and a line vector T. So if I can redraw. So now I'm actually trying to show the half plane. So if this is the half plane, as you know, the bottom edge of the half plane, this is the dislocation line, and along the dislocation line we can take a unit vector parallel to the dislocation line. That's the so-called tangent vector, which I represent by t hat. And then if I use right hand finish to start convention for assigning Burgess vector, then you will find that a Burgess vector B equal to 1 interplanar spacing in this case, pointing to the left, will be associated with this dislocation line. Now, this is the slip plane. This is the slip plane of this dislocation. The plane containing the line and the Burgess vector. Suppose that this dislocation moves to the left. This dislocation moves to the left. So let me show the direction of the movement by another unit vector d hat. So a dislocation with line vector t, Burgess vector b is moving in the direction d. So if this dislocation moves in the direction d and comes out, you can see that finally this extra half plane will emerge on the left edge. The extra half plane will emerge on the left edge. So this shows that the upper half of the crystal has moved with respect to the lower half by one Burgess vector b in this direction. Now, if you see here, the way we have assigned, so the t vector is going in, the d vector is to the left, so t cross d, if you create a vector, so t vector is going in, the d vector is towards the left, so the t cross d vector is pointing up. That's the t cross d vector. So the t cross d vector is pointing up, and so we can say saying up and down can sometimes become confusing depending on the orientation of the dislocation line. So we have to make this up and down also precise with respect to the dislocation. So it's better to say, instead of the upper part of the crystal, that the part of the crystal on the positive side of the vector t cross d. So what we are finding here, that part of the crystal on the positive side of t cross d slips in the direction A, slips by positive b. So we can write this conclusion. Let me write this conclusion for you. Part of the crystal on the t cross d, where t is the tangent vector and d is the unit vector in the direction of motion of the dislocation. So part of the crystal on the t cross d side of the slit plane moves by plus b, an amount equal to the positive Burgess vector plus b. The plane moves by plus b with respect to the crystal on the other side. And although I did this exercise for a positive dislocation moving towards left, actually this result is true either for positive or negative edge dislocation, as well as right-handed or left-handed screw dislocation. In all these cases, so this is a general result, in all those cases, always the T cross D side of the crystal will move by plus B with respect to the other side of the crystal. This is a general result. Thank you.